Today I'm going to be talking about asteroids. And one of the things I do is call it the fossils of the solar system. And the definition of fossil is a remnant, impression, or trace of an organism of past geologic ages that has been preserved in the Earth's crust. And that's talking about fossils on Earth. And these are some of the fossils that one would see. These are sea anemones, Tyrannosaurus rex, trilobites, some ancient fish, and these are clearly fossils that we're used to. Well, these are fossils of the solar system. They're asteroids, and we call them fossils because they're leftover pieces that never formed a planet. But they are very valuable in our understanding of the formation of the solar system and perhaps how life came to be. The other things we look at are they may be able to be used for mining, and I'll talk a little bit about that at the beginning. And they might be a danger if they happen to collide with Earth. And we'll talk about how likely that is and what we're doing to try and prevent that from happening. So the first part is, can they be used? And we're talking about asteroid mining. Asteroids are full of different very valuable minerals, ores, etc. But to try to mine an asteroid would be very complex and very expensive because they're not near Earth. So the only way of doing it would be either very long-term missions to these asteroids and trying to bring back material, and it just wouldn't be worth it. Or trying to capture an asteroid and have it in Earth orbit, which also we don't have the capability of doing at this point in time. But there is one thing that can be used, and that is water. There is actually water that is locked into some of the rocks of asteroids that could potentially be used for rocket fuel. There is one company that is proposing to do this. And their claim is, if you want to explore space, bringing everything from Earth is ludicrous. As an example, the Lewis and Clark exposition that was in 1804 through 1806 explored the Louisiana Purchase, the territory that was bought by the United States. And it went from St. Louis all the way to out to the coast of Oregon. It lasted 863 days, so that's more than 2 years. With a crew of 45 people, they traveled 8,000 miles. And you could imagine if they brought all the supplies they needed from the start, they would have quite a bit of trouble trying to do that. And so what they did is they lived off the land. They had people with them who knew how to do that. And they found shot various game, found various berries and fruits and things growing, and were able to live off the land during this exposition. Well, this company is proposing the same kind of thing in terms of at least rocket propulsion if you're going to go into space. And the timing of when asteroids form is critical. If they form very early in the formation of the solar system, it resulted in high temperatures with complete melting and therefore the vaporization of water. So they would have very little, if any, water locked into the rocks. And you could see that basically these that are close to the sun and forming very early on have very little water in their rocks. But the late forming asteroids, these were much cooler. They were cooler temperatures and allowed more water and other volatiles to be present, locked into the rocks. And so what they propose is solar thermal mining of asteroids. And this is a simulation that they they used to show that you could heat up the asteroids by solar thermal means, obtain steam from them, and use that as rocket fuel, basically, by doing this. So the sunlight would be reflected off. It would heat the asteroid, and that would then could be used as steam coming out of a vent, which would be basically the rocket nozzle, and this would provide thrust for the spacecraft. No one has actually done that yet, but they're talking about the possibility, and they are researching doing it. So the other thing that's more important than that right at the moment are what are asteroids made of and what can they actually tell us? And when we're talking about asteroids, there are two main areas. These are the main belt asteroids that orbit between the orbit of Mars and the orbit of Jupiter, in between them. And there's several million asteroids in this belt. And then there are a number of asteroids that called the Trojan asteroids that orbit in Jupiter's orbit. And Jupiter sort of captured them, but didn't actually have them in orbit around Jupiter. They orbit the sun, but orbit in the same orbit as Jupiter. There are, and we'll get to this later, there are asteroids closer in that we'll talk about a little later, but these are the main ones. So NASA did examine asteroids in the past to some degree. There are some asteroids that survive their entry into the Earth's atmosphere and hit the Earth, and we call those meteorites. And there are investigations of those meteorites on Earth. The problems are that they are contaminated with Earth sample, and therefore one doesn't know if you're examining just the Earth or you're examining the meteorite itself. There was one lander on Eros in 2001. Eros is a large asteroid in the main belt, and that basically examined it. It didn't take any samples or anything, but it examined it with the instruments it had on board. And then one called Dawn launched in 2007, and that orbited Vesta and then Ceres. And that was orbits in around 2015. And these are two of the larger asteroids, again in the main belt. So from this, we learned that there are actually three types of asteroids that we know of. There's the D type, which are mainly rocky asteroids, and they can reach Earth's surface because they are mainly rock. And so they don't completely burn up in the Earth's atmosphere. There's a C type. These are mainly carbonaceous, meaning organic in origin. They do have some rock and some metal, but there's a lot of organic material on them. And because they're loose and mainly organic, they do burn up mostly in the atmosphere. And then there are metal asteroids that have the outer shell burned sort of rubbed off in collisions with other asteroids. And so they're basically all metal asteroids. So how are asteroids formed? Well, this is an artist's conception of the very early solar system. What you see is a cloud of gas and dust that's light years across. In the center, the sun forms, and that takes up most of the material in this gas and dust disk. But whatever is left form these small little planetoids. These are anywhere from several meters to several hundred meters across. And as they basically hit each other, they attracted to each other, and you get more and more of these asteroids joining up, and eventually a planet forms. But once a planet forms, it sort of keeps the rest of the asteroids from forming in that area. And so the asteroids are left over. As I said, the leftover pieces, those are asteroids. The large planets, Jupiter, Saturn, Uranus, Neptune, prevent nearby planet formation. And then the metal asteroids form when a larger body has a collision with another large body, and it leaves one of them with the core exposed. And this is sort of that representation where you have this asteroid hitting a planet or another asteroid, and all of the outer surface of this planetoid, or whatever you want to call it, is scraped away, leaving a metal asteroid. Now, in order to be able to get a better understanding of what these asteroids are, how they formed, what they consist of, NASA has now 3 new missions involving different asteroids. There's OSIRIS-REx. This is a mission that visited a C-type or carbonaceous asteroid. We'll get to that in a minute. This was launched in September of 2016 and actually obtained a sample that was returned to Earth in September of this year. There's a second mission called Lucy, which is a visit to several of the different Jupiter Trojan asteroids. These are the ones that orbit in Jupiter's orbit. And this was launched in October of 2021 and is expected to arrive in about another 3 or 4 years. Psyche is a visit to a metal asteroid, and this was just recently launched in October, and so it'll be several years before it arrives at the asteroid called Psyche. The mission is called Psyche. The asteroid is also called Psyche. So let's talk first about OSIRIS-REx. Basically, its mission was to return and analyze a sample of a carbonaceous asteroid. It also did spectrography of the asteroid, so it could provide information of the entire asteroid population. And it could map the chemistry and mineralogy of a primitive carbonaceous asteroid. So you might ask, why do we pick a carbonaceous asteroid? Well, the asteroids with carbonaceous characteristics, so the C-type asteroids, make up somewhere between 1/4 to 1/3 of all the near-Earth asteroids. These are the ones that are closer into Earth. But less than 1/30th of all meteorites, because they're less likely to survive the passage through Earth's atmosphere. And they're also more likely to get contaminated if they do get to the ground. So they're really special. And that's why NASA wanted to go there and get a sample and see what's what. They also may be special if you think there could be a connection to the origin of life, and we'll talk about that in a minute. There is one exception to the rule in terms of landing, and this is the Winchcombe meteorite, which was a carbonaceous meteorite. It happened to land in a driveway in England in February of 2021, and it was a very dry day. There wasn't any contamination, basically, and it was recovered in pristine condition. And they got a total of 602 grams, which is not a lot, but it's close to maybe 3/4 of a pound of material. Thinking the asteroids are tons of material, it's a tiny bit, but it's important because it's one of the few asteroids that we were able to get in pristine condition like this. So far, what we know about it is that it's about 11% by weight of extraterrestrial water. So it has a lot of water locked into the rocks. And this is one of the things about carbonaceous asteroids. And it also has a lot of carbonaceous material, including amino acids. So these could be the sort of fundamental building blocks of life. And this is what this material looked like. This is in after it was collected off that driveway. Now, OSIRIS-REx, going back to it, its target is Bennu, which is a sort of mid-sized asteroid. It's about 492 meters across. So that's sort of about a quarter of a mile across. And it's spheroid in shape, and it's like a spinning top. You see that there. And Bennu is one of the near-Earth asteroids, and so it orbits between Earth and Mars. And we'll get to more of those later. So comparing some others, Hayabusa and Hayabusa 1 are slightly larger. Bennu is sort of in that class, though. And this was the spacecraft, OSIRIS-REx, that went there. It had a lot of instruments on board to be able to detect what was on the asteroid and find an appropriate pace to get a sample. That was the main mission, to get a sample. And this was the sampler that went down onto the asteroid, got a sample of it, put it into this container that then went back to Earth. And I'll show you that in a minute. So this is on Earth, but shows how the sampler works. It touches the surface. It pushes out an amount of nitrogen gas that blows things around and into the sampler, which then lifts back off the asteroid and puts it into the container. And basically, that's how it works. So this was the place where the asteroid was going to be sampled. They looked at a lot of different places, finally decided on this area because it was an area that was a little less fraught with danger, let's say. There were a lot of areas that had big rocks next to them, or even almost mountains next to them, where there was concern about getting the asteroid, the spacecraft in there and sampling. But they wanted an area that had water, and this was seen by these hydrated compounds, which means that there was water locked in there, as well as these areas with organic material, and so that it could take a sample of that organic material back to Earth. This was the expectation, that it would hit the surface. It would be a hard surface. It would blow out that nitrogen gas, so that stuff would blow around and back into the sampler. They expected about 60 grams of material. This was the reality. It's loose enough that it buried itself into the asteroid, still blew out the stuff, and then lifted off from the asteroid. The total amount of material that was collected ended up being about 250 grams. And you see that here, where after it's lifted off, there's still lots of stuff floating around. So the amount of material that was collected was almost 5 times the amount they were hoping for, which was a really great sample. And then after it was collected, it's placed in this container, which then, as the spacecraft gets closer to Earth, it launches this container, which then enters Earth's atmosphere and is collected. And you see it here. It was released. This was the peak area of deceleration and heating. And then once it slows to an appropriate velocity. Up here, it's at 25,000 miles an hour. As it slows down to less than 200 miles an hour, the parachutes deploy and it gently touches down on the surface. This was successfully done. It was then successfully transferred to NASA Johnson Space Center, where it's being evaluated. And then 1/4 of the sample will be sent to different laboratories all around the world. 3/4 of it will be stored so that in case there are better instruments later on, they can still have a sample to analyze. And there's 63 analysis techniques that are being used. I think, and as I said, 75% saved. But I think the most exciting are basically the electron microscopy and looking at the mass spectrometry, looking at a small scale to be able to see, are there amino acids, are there other nucleotide bases, things like that on this asteroid that could be the spark for life back at the beginning of time of our solar system. So they're going to be analyzing 25% of the sample with hypotheses looking at how does the sample compare with the observations from Bennu in terms of the mineralogy and chemistry, for example. And most important, as far as I'm concerned, at least, being a former biology major and physician, is does the sample contain organic compounds that could have influenced the origin of life? And we're talking about amino acids, the bases of RNA and DNA, things like that. Just to give you a new update, that's really exciting. And this is a different spacecraft. This was the Japanese spacecraft Hayabusa 2, and it explored this asteroid called Ryugu from June of 2018 to November 2019. And then it returned a sample of this asteroid. Sorry, that should be asteroid, not comet. And that was about 5 grams worth. But the thing that they recently found after examining all that material was that uracil was found in this sample. Now, if you are either a present or former biologist, you'll know what uracil is. It is in other things like vitamin B12 and other things, but the most important thing it does is it's part of RNA. It's one of the bases of RNA in place of a different base in DNA. So it acts as messenger RNA. Well, okay, so messenger RNA, so what? Well, what we think is that RNA initially was the genetic material of early life on Earth, of simple life on Earth, and that it was incorporated into other cells and became messenger RNA. But the original RNA was probably in the early life. And so if you have one of the bases, uracil, on an asteroid, if you find the other bases on another asteroid, with them forming together and forming the planet Earth, it's entirely possible that all of the necessary items for simple early life on Earth were there. This is an extremely exciting thing, at least as far as I'm concerned. The other thing we want to know is, what does the sample tell us about the history of the solar system? Remember, we were talking about the pre-solar material and the protosolar disk. And we're hoping to be able to find out things about it from a piece of it that formed as an asteroid. So another mission that's ongoing now is Lucy. That was launched in October 2021. And you see that it was a nighttime launch, and this is that spectacular launch. It's named Lucy because in honor of our earliest human ancestor, with whose fossil was found in Ethiopia, and the Ethiopian, anthropologist who found this fossil in Ethiopia named it Lucy. And so the mission is named in that fossil's honor because our Lucy, that is the one that's the spacecraft, is going to be going to these asteroids to look at the sort of fossils of the solar system. And where it's going to be going is to these Trojan asteroids that have never been explored before. These are the ones that orbit in Jupiter's orbit. And the hope is that it's going to teach us several things. One is the very early solar system formation, like how these asteroids formed in the gaseous disk and what they consisted of, what was in this disk that made these asteroids. And also then early planet formation, the four inner rocky planets, meaning Mercury, Venus, Earth, and Mars, and the four giant planets being Jupiter, Saturn, Uranus, and Neptune. And hopefully we're going to get some more information about all of that. So the things they want to know are what rocky and icy materials make up the giant planets. How and where did these giant planets form? Did they form out further in the solar system or closer into the sun in the solar system and then move around in the solar system? Or did they form in the area where they actually are now? And then the other thing is, how did the materials needed for life make it to Earth? And we're hoping that some of these asteroids will give us information about that by us finding, again, more carbonaceous material on them. How some of these planetismals happened were those that were, there are some planetismals that were actually ejected from the inner or even outer solar system and became part of the Kuiper belt or beyond. And we're going to talk about that perhaps next year, about what the Kuiper belt is. It's the belt that Pluto is in. And then some of the ejected planetismals got into become the main asteroid belt, but some of them probably were those that were captured by Jupiter and ended up being the Trojan asteroids. So this is a record-breaking number of asteroids that are going to be examined. The initial plan was to examine 6 of these Trojan asteroids, going from one to the other. Now, they're not going to bring any samples back. The spacecraft will orbit each of these for a time, taking or fly past them, getting a lot of information as they do so. But they will not be bringing back samples. There are enough instruments on board that are going to give us a really good look at what these asteroids consist of. So these are the asteroids. There's Eurybates. You'll forgive me if I'm not pronouncing any of these correctly. If you're a Greek scholar, I'm sorry about that. But Eurybates and Keita are, Eurybates is the asteroid. It turns out that it has a tiny little moon that orbits at Keita, and so it will look at both. And this is a gray asteroid, which means probably more carbonaceous material on board. There's a red asteroid called Pale-Mele, and it also has a small moon that orbits it. And this is more red, so it has probably both rockiness as well as carbonaceous material. There's Lucas, which is very red, so probably mostly mineral. Orus, which is very red. And then these two, which are very close to each other and orbit around each other, called Patroclus and Menoetius. So these are binary asteroids because they orbit each other. And most asteroids are thousands of miles apart, or even more. These two are so close that if you stood on one, you'd see the next one next to you. But these will be then evaluated at the same time. And it's going to be able to do this, beginning with the first one and ending with these two last ones in only 15 months' time. It does take about 6 years to get there, but it will only take 15 months to do the entire tour. Hubble has been able to get at least a glimpse of these. For example, Eurybates and Keta, they imaged, they knew that this was Eurybates, and then a small little image there, Keta. And the same thing with Patroclus and Menoetius, that they orbit each other because it was able to see how close they are. The Trojans' main physical properties are that they're dark, even darker than charcoal. And so they're going to be evaluated somewhat in visible light, but mostly in infrared. They exhibit a wide range of colors, from gray, which are the C type, the carbonaceous, to very red, the D type, or rocky type asteroid. Some have satellites and odd shapes, meaning that they may have hit each other or collided together or all kinds of different things and we'll be able to get an idea of how they formed. And interestingly, the estimated density ranges from 0.8 grams per cubic centimeter, which is less than water. So there's a lot of air or space anyway, or water itself or other volatiles in them, up to 2 grams per cubic centimeter, which is about the density of limestone. So that's why it's important to get a lot of different asteroids under our belt. The spacecraft is about 15 feet across, and it's mainly the solar panels that make it up, because it's going to be far enough away that it needs the solar panels for energy. But on board the center of it, it has a lot of instruments in its suite, and these will be able to look at things like the gravity there, whether it has any magnetic impact, or also spectrometry and things like that. So Eurybates, as I mentioned, it's the survivor of a massive collision. That's what's believed anyway. And it belongs to an uncommon spectral type. And we believe it's the parent body of an asteroid family formed in a large catastrophic collision. That's partly why Keta is there. It's also just looking at it from afar, it looks like that is the case. And you can see it here. It was the Hubble Space Telescope, as I said, that found Keta. We know it's eccentric in terms of its major axis, and that's part of why we think it was a collision. Polymele is the second target, and that's a very red asteroid. Lucas is a strangely shaped asteroid. You see that it's sort of this weird shape with a hole in the middle. Again, that may give us information about how it was able to form, why it formed in that way, and probably from collisions. Orus is the reddest of them, meaning it's the most rocky type of asteroid. And that'll give us information about that kind of asteroid. And then these two, Patroclus and Menoetius, are the two that orbit each other, and we'll be able to hopefully get some information about why it is that these two would be able to orbit each other, and is that part of the whole formation concept of asteroids. And you can see they're both red, both binary, so they're both rocky, very similar in shape and size. So it's of interest to be able to look at them. Now, one of the interesting things is, as I said, it was launched in 2021 and it's on its way. But they found something, and that is that Lucy would have passed within 69,000 kilometers from a main belt asteroid called Dinkinesh. And that was just too good an opportunity to let go. Because now we can compare all the Trojan asteroids that we're looking at with a main belt asteroid. And so they adjusted the trajectory to fly by it at only 425 kilometers and get a good look at it. It is the smallest main belt asteroid visited by any spacecraft so far. You can see that these others are in the generally 5 to 12 kilometer range. The near Earth asteroids are more in the several hundred meter asteroid, which is what Dinkinesh is. So it's of unusual kind of thing. The other interesting thing that we didn't know until it got a little closer was Dinkinesh has a moon itself. This is the moon. It's not attached. It just looks that way. But this is the moon orbiting Dinkinesh. And we got an even better look. We found that Dinkinesh's moon has a moon. These are binary moons orbiting each other while they both orbit Dinkinesh. And so this is going to get a really good idea of asteroid formation. And then finally, Psyche is the journey to a metal world. This is an artist's conception of what it might look like. And the testable hypothesis that we think is true is, the question is Psyche the exposed core of a larger differentiated body? And this is the sort of advertisement that NASA is giving. But basically, if you think about it, this might be the path for Psyche. All of these asteroids come together, form eventually a planet with a core, a mantle, magna, and crust. But if it's a smaller piece, for example, it has a metal core, and then it hits something, the outer rim of rocky and carbonaceous material is scraped off, leaving that metal core, and that may be what Psyche is. Originally, it was scheduled to launch in 2027 because of a delay, but NASA and JPL were able to catch up, and it was just launched recently in October. It'll have a cruise with a gravity assist of about 4 years, so it should arrive at Psyche at about 2027 instead of 2031. When there, it's going to do several orbits of Psyche, again, getting information through its magnetic field measurements, imaging and mapping, topography, meaning imaging again, and geologic mapping, and spectrography. So it'll get gravity mapping, magnetic mapping, etc., and composition mapping. And this will tell us exactly what it's made of and how it formed, hopefully. So the last piece of the talk is about, are asteroids a danger, and how can we defend ourselves if they are? This is an image of the sun. You see it as a star because there's a way to block out the sun so you can get imaging of all the other things around it. This is Mercury, Venus, Earth, Mars, and you see most of these asteroids are between Earth and Mars. These are the main belt asteroids, but the near-Earth asteroids are right in between us and Mars. So how often do you get an impact on Earth from one of these big guys? The rough estimates are you're talking about an asteroid that's 5 to 10 kilometers in diameter, happening about every 100 million years. These are the ones that exterminated the dinosaurs, for example. A 1 kilometer asteroid every 500,000 years. And then these are things that would wipe out life in maybe a continent. 300 meters, maybe a few every 1,000 years. And these are large enough to wipe out a city. So this would take out, for example, Paris. I'll show you why that I'm mentioning Paris in a minute. No, I'm not against Paris. I love Paris. And then 20 meters, which would do damage but not take out a city, maybe about every 100 years. And that's the one that exploded over Tunguska in 1908. So the near-Earth asteroids, called NEOs, are the ones that are within 100 million miles of Earth. That's about the span between Earth and the sun. And in that area, there are about 30,000 asteroids. The potentially hazardous objects, the ones that are close, within 4.5 million miles of Earth, and greater than 140 meters, so able to take out a city, there are about 2,300 asteroids in that area, but most won't be in the next 100 years. There's only about 17 that could possibly hit Earth in the next 100 years. So it's not a huge danger, but it is somewhat of a danger. And we're talking about, for example, I mentioned Paris because this is Paris. You notice the Eiffel Tower. You're talking about asteroids that are 1.4 kilometer in size, being this big compared to the entire city. Now, it's not just the thing hitting it, it's also the energy it has when it hits. One that's 1.4 kilometers, as I said, would probably take out a continent, not just a city. Again, another one, 1.1 kilometers. The ones that we worry about this is 370 meters, are the near-Earth asteroids, and that's a little bit bigger than the Eiffel Tower. So we need to know not only when these impacts could occur on human timescales, but how bad they'll be. So when the details of when, not just in sometime in the next 100 years, but specifically exactly when, comes from finding the object and determining good orbits for them. How bad comes from measuring the impact energy. And we know impact energy as its mass times velocity. Well, its velocity comes from orbit, but most orbits are about the same. And they're coming in probably about the same speed. So therefore, the density is the mass is the density times the volume. Again, the density varies, but the impact energy depends strongly on the size of the thing. And that's why we say greater than 140 meters, because that's the real danger. And so Congress has passed the George E. Brown Survey Act, which says NASA should discover greater than 90% of near-Earth objects larger than 140 meters by 2020. Well, there have been lots of studies done, including the planetary decadal, which NASA does every 10 years. And of the 25,000 near-Earth asteroids, or 25,000 or so near-Earth asteroids, greater than 140 meters, only a third of them have been found to date. The rest are undiscovered. So NASA is putting together something called the Near Earth Object Surveyor. And that's a planetary defense mission designed to detect, track, and characterize all small bodies throughout our solar system. And it will provide information to anybody who must assess the risks of near-Earth impacts to Earth and also identify potential mitigation strategies. So it's optimized for finding these things, both as individual objects as well as populations. And it's expected to discover greater than 300,000 new near-Earth objects, as well as millions of main belt asteroids. And is a significant improvement on what we know of today. The way it's going to do this is by using infrared. These asteroids are intrinsically bright in the thermal infrared wavelengths, but are very, very dark in the visible wavelengths, so we can't find them. So we can measure sizes and see where they are by using infrared. So the telescope and instrument are passively cooled. They basically have a shield over them so that they aren't exposed to the sun very much. And they have these two infrared channels viewing it at the same time. They're going to be located at one particular spot called the Lagrange point. This is where the sun and the Earth's gravity offset each other. And it's predicted to have at least a 5-year lifetime with a 12-year lifetime goal. And it's going to be launched hopefully in 2026 or 27. It's being built as we speak. The Lagrange point 2, L2, is where the James Webb Space Telescope is located. So this orbits in around L2. L1 will be the Near Earth Observatory, and that'll be in this area. So yeah, James Webb is here. James Webb Telescope is here. Surveyor will go here. So mitigation strategies work best if you get an idea that something's coming early on. This is a graph that shows the kinds of things you can do, and this is the amount of warning time. This is the diameter of the thing that's coming. And you can see, you can always use civil defense. But anything in the range we're talking of, like 100 meters across, requires at least 2 to 5 years. And the bigger it is, the more time you need. So deflection, for example, hitting it and just deflecting it off its orbit, you need about 20 years ahead of time to be able to make some kind of a difference. You can use a 1-ton kinetic impactor. That's very feasible given the launch scenarios we have now. But the problem is that if you do it only 7 years out, there were a lot of they sort of programmed the computer to see what would happen. And there were multiple missions launched by computer, and some failed. For example, in one of them, an asteroid was deflected and Denver was saved, but a very large fragment hit New York City with a 1 megaton blast. So, oops, sorry, New York is gone. That's the problem. To be able to do something really meaningful, you have to have about 20 years ahead of time. When you get down to 6 months out, which the various science fiction movies have shown happening. The only reasonable thing is evacuation of the damage zone. That's the only thing that's feasible. You cannot do anything else in terms of avoiding the asteroid hit. So in summary, there are millions of asteroids in the solar system. We know about the main belt asteroids between Mars and Jupiter. We know about the Trojan asteroids in the same orbit as Jupiter, and then the near-Earth objects within 100 million miles of Earth. These can give information about the solar system, including formation of the solar system, and maybe how life formed on Earth. They may be utilized someday for rocket fuel, using the water in them. And they do pose a hazard to humanity, potentially anyway, but NASA has plans to try and avoid that danger. And with that, I will take questions.
Thank you so much for this presentation. I'll go ahead and open up the floor to questions. Okay. You can either put them in the chat or raise your hand, unmute yourself. I think we're a good sized group that you can just unmute yourself as well. I'm not seeing any. Clint, how close will Lucy be from each Trojan asteroid?
That's a good question. The plan is to have them about 100 meters or a few hundred meters away. So less than a quarter mile from it. And with that, they'll be able to get a good examination of it with the instruments that are on board.
As a follow-up, why stop Lucy after 6 asteroids since it has its own solar system?
That's a good question. NASA's planning for 6. I will tell you that JPL and NASA always builds things better than they need. For example, Curiosity, the rover on Mars, was expected to do its thing for only 2 years on Mars. It's now been 11 years and still going. Part of it is that you need enough fuel to be able to go from one asteroid to the other. I don't know how much fuel is on board and whether they'll have fuel left after they go to the last 2 binary asteroids, whether there'll be extra fuel to go to others. If there is fuel remaining on board, yeah, they'll probably try some other asteroids. That's the main sort of thing that would prevent them from doing anything further.
Thank you. Other questions? Eileen, go ahead.
Hi, that was a super wonderful talk. I really enjoyed it. Could I ask a question about the moon landings?
The moon landing?
Sure.
I read that U.S. is expected to land in 2024, 2027, and are both countries likely to meet those goals?
Okay, so say again, who in 2024?
I thought it was the U.S.
And who in 2027?
China.
Okay.
2030, I think it was for China.
Okay. Yeah, it was 2030, I believe. So in terms of the U.S., no, we're not going to be able to land in 2024. That was never the plan. The plan was to have Artemis 2, which would be the first manned moon mission since we left the moon 50 years ago. But it would go actually a loop around the moon, 40,000 miles beyond the moon. So it would be the deepest anybody's ever gone into space. And then come back to Earth. The actual moon landing itself was initially scheduled for 2025. NASA is still saying 2025 to 2026. It depends on how things are going in terms of building the moon lander, which is still being built. So we don't know yet.
And what about China? Is China going to make their deadline?
Again, it depends on China keeps everything secret. So we don't know where they are in terms of building the spacecraft that would go visit, as well as the moon lander that would visit. So we have no idea really.
Are they planning to land in different spots from the US?
I would think probably not, since the water has been found at the poles, and I think that that's where probably everybody's going to be headed. Whether it'll be the North Pole instead of the South Pole, I don't know.
Thank you very much.
You're welcome.
Thank you, Eileen. A question from Patricia. Longevity raises a question about the Hubble telescope. How long is that expected to last now?
That's a good question. We have no scheduled future repairs and servicing of the Hubble telescope like we've had in the past. That's why the Hubble telescope has been so long in its functioning, is because we could go visit it and service it and repair it and do whatever was necessary. We no longer have any missions going there. We have missions going to the ISS, but not servicing the Hubble telescope. So it's a good question. It just depends on how long its instruments, et cetera, are going to last. That no one knows. But in the meantime, we have the James Webb telescope, which is giving us tremendous information about the universe.
Great, thank you. And then how large was the Russian asteroid that hit a few years ago?
The asteroid that, the Winchcombe, you mean?
I'm not exactly sure. Clint, which ones are you talking about?
Yeah,
You
the
just
Winchcombe
mentioned-
asteroid that hit England, it was just a few meters across. So it didn't do any damage really. Put a hole in the driveway. That's it.
Okay. Clint comments, I think the Russian one exploded before it hit the ground.
Yes, it did.
Okay.
That's the one that I mentioned in Tunguska. It exploded in the atmosphere. That was in 1908. It exploded in the atmosphere, but they believe it was probably about maybe 50 meters across, something like that. 50 to 100 meters, somewhere in that range.
Okay. Any other questions before we end for the day? I do want to quickly share a flyer for our scheduled docent-led tour of the Air and Space Museum, where Dr. Farber actually docents as well. We have this set for Thursday, December 7th at 11. And if you'd like to join us, make sure to RSVP. It's $12 a person, but spaces are limited, so please reserve your spot today. You can do so on our RA website. Dr. Farber, since you do docent, is there anything you'd like to share about the museum that they might be interested in visiting?
Sure. I mean, the museum is all in different sections, sort of. So obviously my particular interest is the space gallery, which is really kind of cool. We do have an Apollo 9 command module that's real, and some other real artifacts that you'll be able to see in the space gallery. Then we have World War I, where we have 2 aircraft that are actually original aircraft from World War I, as well as a number of reproductions. And then the golden era of space flight, which has several real artifacts from the 1910s through the 1930s. And then World War II has a number of original World War II aircraft. So there's really very cool stuff there. Unfortunately, I have to admit, I'm not there on Thursdays, so you won't see me there. But some of my the other docents that I docent with will be there on that morning.
Okay. Well, we'll look forward to attending this event, and thank you so much for the series of lectures you've given thus far. We'll see if we can reschedule you or schedule you again for this coming year. I think these are very interesting ones, and I do know that you have a lot of other topics that might be of interest. Thank you.